Well, today we're going to be looking at some more applications of exponential and logarithmic functions. So by now we've explored a great deal about the structure of the table and the graph and the formula. In fact, various forms of the formula for both exponential and logarithmic functions. We developed some algebraic techniques and some technology techniques to manipulate exponential and logarithmic expressions, some properties of logarithms and things like that. And so we can use that to solve equations that contain these expressions. And so now we're going to finish with several different real-world applications of these exponential relations, exponential and logarithmic functions. And I'm going to start by deriving a shortcut formula for finding the percentage remaining in an exponential function, whether that's growth or decay. So recall that we have these three basic forms of an exponential function. Y equals y sub 0 b to the x, which also equals y sub 0 1 plus r to the x, or y sub 0 e to the kx. Come on. So let me go ahead and switch back to the generic letters here. So y equals y sub 0 b to the x, let's look at it in that form. If that's also equal y sub 0 e to the kx, notice if you divide both sides by y sub 0, you get b to the x power is e to the kx. Okay? And b to the x power is e to the k to the x power. So they both have x powers on the outside, so that must mean the bases are the same, that b is e to the k. Well, if you solve that for k, we get k as the natural logarithm of b. So those last two things there are pretty important. They tell us the relationship between b and k. Okay, and of course we can go a step farther. So then k is the natural log of, well, b, remember, is also 1 plus r. So that's also e to the k. Right? And then we also have, of course, k is natural log of b, but natural log of b, b is again 1 plus r. So we could rewrite this as b as 1 plus r, or r plus 1, either one. So we see that r and k are not the same thing, but they're related by this expression k equals the natural log of 1 plus r. So the main thing to remember is just the k is the natural log of b, or remember b is e to the k. Either one of those is really saying the same thing. You should be able to get from one to the other. So let's consider a substance that's decaying or growing exponentially, such as a radioisotope decaying, or it could be anything here. So the quantity present at any time is going to follow this formula, and I changed the letters now to Q for quantity for the y, so then it's Q sub 0 instead of y sub 0, and T for the x because it's time here. So if P is a percentage of the original amount remaining, you take that percentage times the original quantity, and that's how much quantity you have. For example, if half is remaining, P would be 0.5. You take 0.5 times the original quantity, and that tells you how much quantity is remaining. Or this works for exponential growth too. Let's say something's growing and you want to find the time till it gets 3 times as big as it started. P would be 3, so 3 times Q0 would be the amount that you have. So on the one hand, we know that the quantity is P times Q0, but on the other hand, we have the quantity is Q0 times e to the kt. So we have both this equation here and this one down We have the equation up at the top and the equation down here. So they're the same q both cases, so we just put them equal to each other. And this is very important right here. Notice that I divide both sides by q0 and it cancels out. This gives us the equation p equals e to the kt. Notice the q0 cancels out. So it doesn't matter how much q0 is. Doesn't matter how much you start with. So now we take the logarithm of both sides. Log of p equals log of e to the kt. These are the same base on the right. So we get log of p equals kt, or in other words, just rewrite p equals e to the kt as logarithm form. That's log base e of p equals kt. So that last equation there is going to be, let me box that one in. That's going to be very important there for us to, maybe even worth remembering. Okay, we can actually derive it pretty easily if we need to, but it might be worth memorizing that. So, notice again, it does not matter how much we start with. Okay, so let me give you a couple examples here. Suppose we've got some radioactive isotope. Let's say we've got some radioactive plutonium here. Okay, and somebody has a handful of it, and it's decaying exponentially. Well, somebody else has got a truckload of the same substance. Well, the truckload will be half present and half gone exactly the same time that the handful will be half present and half gone. It has nothing to do with the amount you start with. It has to do with that rate of decay, which is the same for both substances. Okay? Or let's take something that's growing. If you invest in a CD, let's say it's paying 2% compounded monthly. It's going to double in value at the same amount of time, regardless if you invest $10 or $10 million, it's still going to double in the same amount of time. Again, it doesn't depend on how much you start with. It depends only on that rate being the same. Now we have this expression, ln of p equals kt. We can solve that for k or solve it for t. Solving for k, you just divide both sides by t, and we get k as ln of p over t. We would use this form if we knew t, but we didn't, and p, but we didn't know k. For example, if you knew the half-life. If you knew the half-life of some radioactive decaying substance, what you know is the time, and of course you know it's a half-life, so you know half is remaining, so you know p is 0.5, and you know the half-life t, then you can use this to solve for k. Of course, once you solve for k, now you've got your equation if you just know some initial amount. On the other hand, we could solve ln of p equals kt for t. Just divide both sides by k. So now you could use this form. If they tell you k, or if they give you the formula, you can solve for any time if you just know the percentage remaining. And so we've actually already done the solving up above in general, and so we can get this is a little shortcut formula. It's pretty easy to use. Well, what if they don't give you k? What if they give you b? Well, k is the natural log of b, so you could rewrite that as ln of p over ln of b. Okay? And, of course, that's actually also, change the base formula, that's log base b of p, but in a real-world application, you're going to want it in the form of a natural log anyway, or either natural or common log. We're going to use natural logs. And b is 1 plus r, so you might see it ln of p over ln of 1 plus r. So if you're given r, use the last version. If you're given b, the middle one. If you're using k, give the first one. And then you can find the time it takes to get down to or up to that percentage, whether it's decaying or growing. In a real-world problem, you're going to actually find b first if you're collecting data. Okay, if you're actually starting from the data stage, because you're going to collect some data, make a table, find the b, which is y2 over y1 to the power 1 over delta t. If that's the same every time between successive points in your table, you have exponential growth or decay, and we found b, and then you could use the middle problem there to go ahead and solve for time there if you know the percentage you're looking for. However, in many real-world problems, you might be given K, you might be given B, you might be given R, or you might be given some specific time and have to solve for K's. But probably the easiest thing for me would be to just memorize this first version, ln of P equals KT, and just go from there. So, here's an application. Okay, let's go down here. Half-life of a radioactive substance decaying exponentially. So this is a specific time where we know the percentage remaining. So the half-life is the time until 1/2 remains. It's always not what remains, not what is gone, but of course if it's a half, it's half remaining and half gone. So what's the formula for the amount of a radioactive substance with initial quantity 500 grams and half-life 25 years? Notice since we're given the half-life, we can find K regardless of what the initial quantity is. The K is going to be the same. ln of P is KT, so K is ln of P over T. T is 25 years whenever the percentage remaining is 0.5. So K is ln of 0.5 over 25, and we'll actually use it that way rather than the decimal version. But if you look at the decimal version there, of course it's log of, the natural log, remember, is a negative, the basic natural log there is a negative number between 0 and 1, and of course log of 1 is 0, log of a bigger than 1 is positive. So when we see log of a half, that's going to be a negative number, divided by 25 is negative. By the way, K does have units. It's per year, so whenever you're using this formula, the T must be measured in years. Okay, which makes sense in this problem. Okay, and so we write down the formula is initial quantity, 500, e to the power natural log of 0.5 over 25 times T. And of course that natural log of 0.5 over 25, K, is approximately negative 0.0277. So in other words, about a little under 3% per year compounded continuously. Once you have that formula, then you can do all kinds of different things with that, including, whatever. You can graph it, you can put in a T value and find a Q value, you can put in a Q and find a T, and so forth. Okay, so here's an example for you, a few examples. I'm actually not going to go over the solutions here in this video, but I'll let you work on these. Radioactive substance with initial quantity 595 grams has a half-life of 32 years. Find the K, the rate of decay. Find a formula for the amount present. Then we'll do one each of an X, and we'll give an X, find a Y, give a Y, find an X. So for the first one, find the amount present 2 years after the initial time. So there's an X, and you have to find the Y. When will it decay to 500 grams? There's a Y, and you have to find an X. You can actually do that algebraically, and you can also do that with technology. A substance that decays at an exponential rate of 5% per year starts with 600 grams. Find a formula for the quantity present T years after the starting time. And how much is present 5 years after the start, and what is the half-life? So this one, so the first one, we knew the half-life, and we had to find K so we could find the formula. In the second one, B, it's the other way around. We know since it says exponential rate, so this is K, and we have to find the half-life backwards. Here's one that's growing. Part C, a certificate deposit is open, earning 3% annual interest compounded continuously, so this is K. How long will it take the CD to double in value? How long will it take to triple in value? So there are a few examples. Let's look at another application of this extension of this application of radioactive decay. So we can use the formula applied to radioactive decay of the isotope carbon-14 to establish the date of death of things that were once living. So carbon-12 is actually the standard version of carbon, the more stable version. Carbon-14 is a mildly unstable version. It's mildly radioactive, and it will radioactively decay and turn into carbon-12. It has a half-life of 5,730 years, so it's not a real highly radioactive substance. And it turns out that it's continuously created in the environment. And the idea behind carbon-14 dating is that carbon is one of the main components of all living organisms. It's also a main component of the air we breathe, and the carbon dioxide, and especially as we breathe out. We breathe in, we eat things, we eliminate waste. Okay, and so what's happening is we're always in this process of continuously replacing carbon-14 in the bodies of all living things, whether it's plants or animals. So the percentage of the total carbon in the organism is the same as the percentage in the environment, and that's a constant, and we've assumed that that's been constant for many years. So what they do is they can take something that's if they could test something that's tissue that's alive, we would find the percentage of carbon is the same. We know what that percentage is. But it turns out that when the organism dies, then it's no longer replacing the carbon. It just has the carbon it had at the point of death, and that carbon-14 gradually over time turns into carbon-12, and that percentage of carbon-14 is going to decrease. Okay? And it's going to do it exponentially with a half-life of 5,730 years. So knowing the half-life, we can compute the K and figure this out. So here we've got it worked out down here. So K is natural log of 0.5 over 5,730, because in general K is the natural log of the percentage remaining over the time to get to that percentage remaining. Well, the time to get to half left is the half-life. That's 5,730 years. And so we get log of 0.5. So that means our quantity is whatever our initial quantity is times natural log of 0.5 over 5,730 times t. So about 0.012% per year. Now, let's think about this just a minute. We were actually given the half-life in this problem. Do you think that's really how it worked out in real world? Do you think somebody sat around watching a lump of carbon-14 for 5,730 years and said, hey, you know, half of this is left? Well, of course they didn't do it that way. What did they actually do? Well, there's a couple things they could have done. They could have watched a lump of carbon-14 for a period of time, not 5,730 years, but maybe you know, every few months for a year, every few days for a year, or something. And then they could use a table of quantity present and time values, and they could use B from the table by, remember, doing a second quantity divided by the original quantity to the power 1 over delta t, or y2 divided by y1 to the power 1 over delta t. That's our formula for B. And they found out that that's the same every time. If so, then they found B. Of course, they could take the log of B to find K, and they could take the log of the P, log of a half, divided by K, and that would be the half-life. Okay, that would probably be the way they could do it. Now, in the case of something like carbon-14, which has a relatively large half-life, what they probably did instead was take some objects of known age. And when I say known age, I mean they know the time the organism died that the object is made out of. Like if it's wood, that's made out of something that was once a tree that was alive. So things are made out of plants, or maybe they have something that was made out of leather that was once a cow, and part of a cow, or something like that. And so and if they knew the time the original organism died that the object was made out of, then they would know a time, and they could test it to see how much is left. And so they basically can make up a table, maybe some wider spread times, but essentially they still made a table of times and amounts left, and we can use that then to solve for B. Solve for B, then you can solve for K. And if you know K, you can solve for the half-life. However, you might see in a chemistry book, you could often see a table of half-lives instead of that. So I just happen to know the half-life of carbon-14, but I didn't really have memorized the K. Okay, so you might be actually given the half-life first by looking it up somewhere. Now, how can we use this to find the amount of time since the death of a once living organism? Okay, well, if we can figure out what percentage they have left, what they do is they actually kind of burn the thing a little bit and they measure the carbon in the smoke, I think, or in what's left, and then they can do it from that way. It does destroy a little piece of this thing, so you don't want to go take some valuable object and have to destroy the whole object. But sometimes you can take a little piece of it that's not so important and use this method if it's important to figure out how old it is. So, couple of things. Realize that this measures not when, not like if it's a piece of furniture, for example. It doesn't really measure when the piece of furniture was made, but rather when the tree died that the piece of furniture was made from. Now, probably it's reasonable to assume that the furniture was made from wood that was made from a tree that had died fairly recently. So the time the furniture was made, the time the tree died, are probably pretty close to each other in time, so that's probably reasonable to assume. But I mean, it is possible, for example, that somebody could cut down a tree, make some wood out of it, let the wood set around for several hundred years before you end up making the furniture out of it. So, keep that in mind. Okay, some other issues I'm going to talk about in a minute. So, we know K is natural log of P over T. Well, K is natural log of 0.5 over 5,730. Well, that is natural log of P over the new time. So basically, you've got this the natural log of 1% over a time we know is equal to the natural log of the percentage we're looking for over the time we're looking for. So if you know either one of these things over here on the right, the percentage left of the time, we can solve for that. So if we want to solve like carbon-14, we solve for this. Let's see, reciprocal both sides, multiply by log of P, or in this case multiply by, anyway, solve for T. You got it like this. It's 5,730 times the natural log of P over natural log of 0.5, and that will be in years. So if we can just figure out the percentage remaining and put it in here, this will solve for how long it's been. So let's try this for an example. Okay, suppose somebody's found something of historical importance like this. This will be both historically and religiously important. Archaeologist claims to have found the cross on which Jesus of Nazareth was crucified. Small sample of wood is examined, is determined that 83.4% of the original carbon-14 is remaining. Can we estimate the age of the cross, and what can we say about the validity of the claim? Well, we can use this formula we just came up with. We put the 0.834 in place of P and work this out on your calculator. We get a little over 1,500 years. Well, wait a minute. That's not nearly old enough. So that's at least 470 years after the death of Jesus, thereabouts. So that's can't be. Claim can't be true. So that tree was still living many, many, many years after Jesus died. So this was not going to be an authentic one. This might be a reproduction from the Middle Ages, but it's not the actual thing. Now, what would happen if it turned out to be the right age? Well, then all we know is the tree that it's made from died about the right time. That doesn't mean it's the right one, but doesn't mean it's not the right one. It just means it could be true because the time is right. So notice you're not really going to be able to establish the truth of a claim like this with just carbon-14 dating, but you might be able to prove it false. And you might be able to say it's a reasonable assumption. Let's do another one. See if you can do this one yourself. A historian claims to have found one of General George Washington's Continental Army uniforms. Now, supposedly this is probably made from cotton, which was once alive, so we could do this sort of thing. In 2002, a small sample of the garment was examined. It was determined that 97.3% of the original carbon-14 is remaining. Estimate the age of the uniform, and what can we say about the validity of the historian's claim? See if you can work this out now. Press pause and come back. Well, again, we use this same formula. Still carbon-14 dating, so we still use 5730 over log of 0.5, then times the log of the percentage remaining, which is 0.973, and that's about 226 years. Well, it was taken, when the measurement taken, it was 2002, so that puts the death of the plant that it was made from in 1776. Well, that's about the right time for such a garment to be made, perhaps. So we can neither confirm nor deny it was actually Washington's uniform, but we definitely do know that it was from about the right time period. Alright, here's some exercises to leave with you. What is the half-life of a radioactive substance that decays at an exponential rate of 2.5% per year? Given a substance that is decaying exponentially with a half-life of 37.6 hours, write a formula for the amount present at any time. Think about your units. What kind of units do we have for our variable t? What percentage of the original amount remaining is remaining at exactly 2 weeks? Okay, by the way, notice we got a unit problem there. Since the half-life is given in hours, we're going to have the variable t is going to be measured in hour, but I asked for weeks here. So you have to do a unit conversion there. A certificate of deposit earning 7% interest compounding continuously. How long does it take for it to double? How about to triple? Your answer is going to come out in decimal years. Take that and make it a whole number of years, and take the decimal part and convert to months. So figure that out to the nearest month. An automobile depreciates at a rate of 16.2% per year. How long does it take the vehicle to depreciate to 1/3 of its original value? Again, give it in years and months. A painting is discovered, and the director of the museum thinks that this is might be by Leonardo da Vinci. Small part of the canvas is examined, is determined that 97.6% of the original carbon-14 is remaining. So we're going to estimate the age of the canvas, and then can we say anything about the director's claim based on that alone? Okay, throughout much of well, I should say the 20th century, the yearly consumption of electricity in the U.S. Was increasing exponentially at a continuous rate of 7% per year. If we assuming that trend held, or holds, and that the electrical energy consumed in 1900 was 1.4 million megawatt hours, write a formula giving the amount of electricity consumption per year as a function of time. And then find out how much electricity was used in 2001, and during what year will the electric consumption of the U.S. reach 4 million megawatt hours. Does that already happen, or will that be in the future? Figure that out, assuming that rate of growth. So biological populations, say bacterial populations, human populations, animals, have a tendency to grow exponentially if the resources are unlimited. So the more organisms that are present, the more babies will be born. Okay? So it turns out that the rate of growth is actually proportional to the amount present. This is exponential growth. So if it happens this way, okay, so that the percentage growth is constant, then that's exponential. So let's look at some population growth problems. Again, I'm going to leave this one for a homework problem. The population of Mexico is modeled by an exponential growth function with a continuous growth rate of 2.6% per year. In 1980, the population was 67.38 million people. So if we assume that growth rate is constant, and it stayed constant, write the formula giving the population of Mexico as a function of time, t be the actual year this time. What is the population of Mexico on November 10th, 2012? See if we can actually figure it out on that specific day, at least according to our model. And what year will the population of Mexico first reach 100 million people? Now let's look at another example here that's interesting. The history of the population of a certain region is given by this table. And I have years from 1980 to 1995 going up in 5-year increments, and I have the population in millions. So see if you can figure out what a formula is for that table. Now, for the first time in modern history, the region had to import grain in 1980. This is a big grain-producing region. They used to export, but in 1980, the population had grown to the point where they had to eat all of their grain and could not import. In fact, they had to import grain to feed everybody. So, following this, they kind of had a wake-up call and said, oh, wait a minute, we got to do something. So they had a vigorous program to expand their agriculture, and the idea is to make their agriculture more effective, and then also just plant more. Okay, and so they tried to decrease their dependency on foreign imports. And so here's what they came up with for the grain production in tons. And just to make things easy, let's assume that 1 ton will for every million people will make them self-sufficient. At least as far as grain. So write a formula for the grain production, how it's growing. Now I'm going to give you a hint. One of these is linear, one is exponential. I'm not going to tell you which is which, but you should be able to figure it out. And at least to the round off there, you should be able to get these to be exactly linear and exactly exponential. Now figure out the grain production per capita. So grain per person, grain per population. You should be able to work out a table there. And if it's 1 or bigger, if it's 1, they neither import nor export. If it's bigger than 1, we're going to say they import or they export. If it's less than 1, they'll import. So what years do you expect a surplus? Okay? And then try to write a little paragraph evaluating the results. Were they successful? Were they successful in the short term? What about long term? And use some graphs to illustrate and support your point. This is a good problem because this is more like a real-world problem than we get from just like one of the little My Math Lab problems where you just fill in a blank. This is something where we have to use what we've learned here actually about linear and exponential functions, put it together. And there's an important moral to this story here as well, because it turns out that well, I'll go ahead and give away. Population has a tendency to grow exponentially, and grain production, food production, has a tendency to grow linearly. If you think about the shape of the graph, what that means in the long term, that's going to tell you that that can't be sustained. So think about that a little bit. Okay? And I think we're going to stop there. I'll print out these problems for you to practice a little bit.